In this video, we're going to look at our two-variance test. But first, let's go ahead and fill in our table. The interesting thing about this test is that instead of the first one being mentioned being our first sample, it will be the group with the larger variance that's labeled with the subscript 1. Also, because the larger variance is labeled sub 1, there's only going to be one tail that we're interested in, and that is the right tail test. For that reason, the only hypotheses that you're going to run across will contain a less than or equal to or a greater than symbol, or an equal or a not equal. And that has to do with the fact that you pick the larger variance to be the first sample. Let's go ahead and fill in our chart. Now, so we're only going to have these two appearances. The test statistic for the F-test of two variances is F equals S sub 1 squared over S sub 2 squared. That's the smallest formula we've had so far. But it does require for this F-test, that is what our table that is a new table that we introduced. You can find it in your tables folder on Blackboard. And another thing that we need to know is that the hypothesis is going to contain sigma 1 squared minus sigma 2 squared. That is what's going to be in our hypothesis. Now, since we have a new table, this new table has 2 degrees of freedom. The first sample, the one with the larger variance, will be N1 minus 1, first degrees of freedom, and the second degree of freedom for the denominator will be N sub 2 minus 1. Don't forget, sample 1 has the larger variance, and that's how you pick which sample is sample 1. Sample 1 has the larger variance, and you'll see that in our example. The next thing I wanted to point out before we look at our examples is if you're conducting a one-tailed test, you will find the alpha on the table. Now, our table has 4 pages, and at the top of each page we have an alpha. If you have a one-tailed test, the alpha is at the top of the page. If you're doing a two-tailed test, though, since you have to divide the alpha in half, you will use alpha divided by 2, or be half at the top of the table. All right? What else? I think that's it. Let's go ahead and jump right in, and we'll build more notes if we need them as we go along. Now, on this first example, I'm going to start by listing the data. A sample of 25 women, so N is 25, had a variance of in their IQ scores of 162. We did a second sample of 18, and they had a variance of 72. Notice I didn't call them S sub 1 or S sub 2 because I have to write them down first. And as soon as I see that the first sample that I took has the larger variance, that's how he becomes sample 1. See, this was the women, and this was the men. I'm comparing the variance in their IQ scores. And I'm testing to see if the women have a larger variance in their IQ scores. Women have a larger variance at an alpha of 0.1. So since this is the claim that's being made, I can now build my null, alternative, critical value, obtained value, and conclusion. That is going to be giving me the alternative. So after I move the sigma sub 2 squared over to the other side, I'm going to get sigma 1 squared minus sigma sub 2 squared is greater than 0. And we'll build the null hypothesis accordingly. Now, it looks just like a normal distribution. This one is a right tail test. Because it is a single tail test, the entire alpha goes into that tail. We need to find that critical value. Remember, it's an F test with degrees of freedom. And it has 2 degrees of freedom. The first one is n1 minus 1, and the second degree of freedom is n sub 2 minus 1. This is for the numerator, and this is for the denominator. So it's going to be 24 and 18. When I look this up in the table, the degrees of freedom for the numerator are along the top. So you're going to look at 24 along the top and 18 along the side. Or actually, no, it's not, is it? I forgot to subtract. I'm sorry about that. We need to subtract 1 from each of them. N1 minus 1 would be 24, and this one would be 17. There we go. So 17, sorry about that. Let me erase it and make it prettier. And intersect, read in, and the number that you should find is 1.83624, and that's that number right there. Now let's find the obtained value. This one is really nice because it has probably the shortest formula. F, let me put a big box around it. F will be equal to S sub 1 squared over S sub 2 squared, which is 2.25 when you put that in the calculator. 2.25 falls over here somewhere. So we're going to reject the hypothesis. So if I'm going to reject the null hypothesis, I have to write what he says. So I'm going to move the the sigma sub 2 squared over to the other side, and I have to say what that says. Okay, well, I'm talking about the variance in IQs of women versus the variance in IQs of men. The variance in the women's IQ scores is larger than the variance in the men's IQ scores. The variance in the women's IQ scores is larger than the variance in the men's IQ scores. All right, let's see if we can get the second one in. The standard deviation for daily sales are given for 2 stores, store X and store Y. Is there a difference in the variances at a 0.05 level? So I know it's going to be a two-tailed test, right? Sigma 1 squared is not going to be equal to sigma 2 squared. That's what that claim is. But I'm looking at my 2 variances, or actually standard deviations. This one is larger, so this is going to be sample 1, and that is going to be sample 2. Let's start. I need to build my null, my alternative, my critical value, my obtained value, and my conclusion. I know based on the claim that this is going to be sigma 1 squared minus sigma 2 squared is equal to 0. Sigma 1 squared minus sigma 2 squared is not equal to 0. It is going to be a two-tailed test. It is an F test. Now, here's the cool thing. You only ever consider the right tail. So this one is going to be blank. You don't ever have to find the critical value for the left tail, just the right. So when I'm looking for the degrees of freedom, I'm going to take n1 minus 1, that's going to be 11, and n sub 2 minus 1, which is 14. In the table that you're provided, there isn't an 11. Look at the numerator. You're going to, well, first of all, let's back up a little bit. Our alpha is 0.05. Since it's 2 tails, I'm going to put 0.025 in each tail. Because you only ever consider one tail, turn the table to the page that has an alpha of 0.025 at the top. That is the only score you're looking for. It's only ever a right tail that we're looking at. So I'm going to do 11 along the top. If you look at the table, along the top it's got a 10 and a 12. And I'm going to go ahead and go down to 14. So I'm looking for one of these numbers. Which one? Because 11 falls exactly between 10 and 12, you're going to pick the 12. The 14 is there, so I'm going to use that. Now, why didn't I use 10 or take the average? You just don't. Now, usually, you will be closer to one number or another. But if it is exactly tied between two, you go to the larger one. And you will find the critical value 3.0502. And again, this is a 4-page table, table F, under tables in Blackboard. Now let's calculate our obtained value. S sub 1 squared. Wait a minute, they're not squared, so I'll have to do it myself. Same thing with the S sub 2. It's not squared, so you'll have to do it yourself. And put that into the calculator. It gives me 1.541. I'll plot that. That falls in the open area, so I'm going to accept the hypothesis. I'm going to accept this. So I'm going to be able to say that the variance in daily sales for the two stores is the same. The variance in daily sales for the two stores is the same. And that's it.